In this example problem, we're going to see if the design shown is sufficient for the span and loading that are shown. So the first step is to find our demand. So we know we have a simply supported beam with a distributed live load. So our shear diagram is going to be as shown here, where we have our reaction values at the ends, so WL over 2, and then it goes down to 0 linearly from there. So since we aren't given any information on the bearings, we're going to assume that the end of the beam is just a point load. So we're going to assume that it's loaded or that is supported by a literal pin at the end of the beam. We can then find our VU of the left support is equal to WL over 2, so 10 kips per foot times our L, 30 feet, divided by 2 is 150 kips. So we're going to use our ACI design assumptions. So we're going to be looking at our critical section, which is D, away from the face of the support, so in this case, D away from the end of the beam. So our VU critical, which is what we'll compare to, is 150 kips, which is our shear demand at the end of the beam, minus our 10 kips per foot, so the slope of our shear diagram, times D, so 35 inches divided by 12 inches per foot to get our units consistent. And we'll find our VU at our critical section to be 120.8 kips. So that's our value right there, so 120.8. So this is the value we'll compare to our capacity to see if our section is indeed sufficient. So our capacity is going to be made up of our concrete component and our steel component of our shear strength. So we can first find our VC. So this is going to be equal to 2 times the square root of our concrete strength, which in our case is 5,000 psi. So remember, when using ACI expressions, we need to use psi under our square root, times our BW, which is 6 inches, times our D, which is 35 inches. And I'm going to divide this by 1,000 pounds per kip to give us our answer in kips. And we'll get this to be 29.7 kips, and that's the contribution of our concrete to the overall shear strength. So next, we need to look at, and also, sorry, I forgot to mention our BW is 6 inches. So we draw our line across the centroid of the section, and we see that the width of our section at that point is 6 inches. So we can also see that the amount of steel that's crossing that plane is one number 5 bar, spaced at 5 inches. So we'll have our AV is the area of our number 5 bar, which is 0.31 square inches, times FY, which is 60 KSI. We have grade 60 steel, times our D, which is 35 inches, divided by our spacing, which is 5 inches. So we'll get our VS to be 130.2 kips. So we can find our phi VN then to be equal to phi for shear is 0.75 times our VC, 29.7 plus VS, 130.2, and this is equal to 120.0 kips. So we need to compare this to our VU. So we found before our VU to be 120.8 kips. So in our case, our VU is greater than our phi VN. So this design is no good. Um, so if we were designing here, our options would be to either add more steel, or we could potentially use the detailed expression for VC. So we use the simplified expression. So if we used the detailed expression, we would likely get a higher capacity and our design would be satisfied. But in this case, our design was no good.